We're going to try this problem out one more time. We are going to find the equation of the plane containing the line x equals 3 plus 4t, y equals negative 2 plus t, and z equals 5 minus 3t, as well as a given point. And the point is 6, 1, 0. So I wanted to talk about what the strategy is going to be when you have the equation of a line as well as a point out in three-dimensional space, and you are looking for the plane that contains both of these things. Now what we're going to try to do with this is determine a point on the line and use the direction vector for the line as a vector that is contained within the plane. We'll refer to that vector as v1. Then if I use the point that's on the line as well as another point that is within the plane, I can refer to that as the vector v2. The cross product of these two vectors should give me a vector that is orthogonal to both of these lines, and we can use that as the normal vector for the plane. So first and foremost, we would have to decompose the given line into a point as well as a direction vector. So the point, we'll refer to the point as p, would be what we get by plugging in t equals 0 to all three of these parametric equations. That would be x is equal to 3, y is equal to negative 2, and z is equal to 5. The associated direction vector, which we just referred to as v1 and will continue to do so, would be the coefficients of t in each of these cases. So that vector would be 4 for the x component, 1 for the y component, and negative 3 for the z component. Now with that in mind, we can determine our secondary vector, v2, by treating the point 6, 1, 0 as our terminal point, and we'll treat the point on the line as our initial point. And like we do, always do terminal minus initial. So this will be 6 minus 3 for the first component. Second component will be 1 minus negative 2. And the third component will be 0 minus 5. Now last time I tried this problem I did 1 minus negative 2 and got negative 3, and I won't be repeating that. So 6 minus 3, that is positive 3. 1 minus negative 2 is positive 3. And 0 minus 5 is negative 5. Thank you, Aiden, for bringing that to my attention. So now we have our two vectors that are within the plane, v1 and v2. We can get our normal vector by taking the cross product of these two vectors. So v1 cross v2, that'll be equal to, across the top row, we throw ijk. v1 across the second row, that'll be 4, 1, negative 3. And across the third row, we'll put the vector v2. So 3, positive 3, negative 5. We'll recopy down the first two columns. Then we go and give it a little slashy, 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 slashy. And as always, slashes that go in the downward direction, we account for with a plus sign. That'll be negative 5 times 1 times I. That'll be negative 5i. J times negative 3 times positive 3. That'll be negative 9j. And finally, positive 12k. In the upward direction, we account for these with a minus sign. That'll be 3 times 1 times k. That'll be 3k. 3 times negative 3 times I. That'll be negative 9i. And negative 5 times 4 times j will be negative 20j. And we'll add up our I components. We have negative 5 down here. That'll be plus 9 up there. That'll be 4 for the I component. For j, we have negative 9 down here. We have positive 20 up here. That'll be 11 for the j component. And finally, positive 12 down here, minus 3 up here. That'll be positive 9 for the z component. Of course, you can check this answer by doing a quick dot product of this vector with either of the original two vectors. That's 16 plus 11 minus 27. That is, in fact, 0. And then 12 plus 33 minus 45. That is 0 as well. So next up will be to come up with the equation of a plane that uses normal vector for 11, 9. And you are allowed to use either of the points that we referenced earlier, either the point that's on the line or the point that's within the plane. Let's go ahead and use the point that is on the line. Ultimately, it shouldn't matter which of these points we're using. especially if we were to get it down into its general form. So this will be 4 times x minus 3 plus 11 times y plus 2 plus 9 times z minus 5 is equal to 0. So once again, standard form of a plane, we take the corresponding component and multiply it by the variable minus the corresponding coordinate. Now, of course, if we were interested in distributing all of these, we would see a 4x minus 12 plus 11y plus 22 plus 9z minus 45 is equal to 0. We could then combine all of these like terms and express our answer in the following form. Let's see, we have negative 57 plus 22, I believe that would be negative 35. If we added that over to the other side, that would be positive 35. And just as a quick double check to our answer, I'm going to take the point that we didn't use, which is 610, and verify that that works out. If we take 4 times 6 plus 11 times 1 plus 9 times 0, we do in fact get 35. So I'm feeling pretty good about this answer.